Okay, so welcome back to another video. So today we have a trigonometric integral, and it consists of a bunch of natural logs and cosine, sine, and tangent. So we have natural log of cosine of x divided by tangent of x multiplied by the natural log of sine of x divided by natural log of cosine of x dx. So as you see, we have a combination of natural logs of cosine of x and natural log of sine of x, as I just mentioned, that if you actually integrate those by itself, like standalone, that it actually gets some nice results out of that. But now it's everything just jumbled together into one. But not to worry, that we can actually just utilize some u-substitutions and integration by parts. A lot of that will be coming into handy and using a bunch of linearity. And once we get to near the end, as we simplify things out, there's actually a couple of special functions that we will be utilizing for a nice answer that we're trying to achieve for here. And it does come down to a nice answer. So with everything in mind, so let's actually just jump right in. So this whole thing will be called capital I, but I'll save that notation for later in a sec once we simplify everything out. So let's actually start off with a u-sub. Well, suppose we let u equals the natural log of sine of x. So differentiating both sides, so I have that du is equal to cosine of x divided by sine of x dx. In other words, this is actually the same thing, can be rewritten as tangent, well rather 1 divided by tangent of x and then dx. And this is nice that we have a tangent of x under the denominator over there, that when we substitute things, that will make things a little bit nice. So we're not just done yet with the u-sub, because for one, we have a natural log of cosine of x, and we have to simplify things in terms to make things into the world of u. So keep in mind that we know that sine of x, as we put this down, is the same thing as equal to e to the power u, as we just do the explanation of the e based both sides. Okay, so in other words, the same thing can be written as cosine of x is written as the square root of 1 minus sine square of x. That's just from the fundamental theorem of trigonometry. So sine square of x, we said that's sine of x. So in other words, that's the same thing as the square root of 1 subtract e to the power 2u. So now that we have all that, so let's put everything back together. So capital I being our given integral we want to evaluate. So we have to change our new bounds, don't forget. So if I plug in pi over 2, so back into over here, that means that's going to approach 0. And if I have 0, so I have an ln of 0, which is undefined, so we can actually say that it's approaching negative infinity. So with this, now let's plug everything back in. So natural log of cosine of x, which is the same thing as the natural log as the square root of 1 subtract e to the power 2u. And then times the natural log of, so substitute ln sine of x, that's going to be u, and then divided by ln of, now just cosine of x, which is the same thing as here, ln of the square root of 1 minus e to the power 2u. So now what we can do is let's actually simplify even further. So I'm applying some natural log properties. So we still have our integral negative infinity to 0. So I have the natural log of the square root of 1 subtract e to the power 2u. I know we can simplify that out, but the main thing is that we want to simplify this even further, and then we can just proceed a little further with the natural log properties of that simplification. So from here, I now have, this is going to be the natural log of u, and then subtract the natural log of the natural log of the square root of 1 minus e to the power u. And so now we can simplify things even further. And because of this, we have to do a little bit of distribution for each of these. And then also jumping on one step a little bit further, that we can actually simplify this even further with applying the natural log properties, that I'll skip to the, that little work and then put everything back together as what it should be. So what that comes down to is that if you apply all this all together, we have 1/2 then times the integral from negative infinity to 0 of ln of u, and then times ln of the square root, or well, we already applied the square root because that's why we have the 1/2 outside. So my mistake, ln of u, and then times ln of 1 subtract e to the power 2u, and then add this with the natural log of 2, and then divided by 2, multiply with the integral from negative infinity to 0 of the natural log of 1 subtract 2, or e to the power 2u. Sometimes it can be hard to get those mixed up. And then lastly, if I just move the one step line below, we have 1/2, and then times the integral from negative infinity to 0 of ln of 1 subtract e to the power 2u, and then multiply with ln of 1 minus e to the power 2u, and then finish it with du. There's a lot going on over here, so what I'm going to do is we're actually going to now pay our focus into this integral over here, because what's nice is that if you reduce all that down, we're going to get some things that's going to cancel out if we go back to original over here. So what cancels out? So let's actually first evaluate what's underlined in the purple. So I'm going to call this integral over here, we'll just call this capital A, and so that's what we want to calculate. So to evaluate capital A over here, so what we'll have to do is we're going to actually apply some u-substitution. So I'm going to put a w for our new variable. So we'll let w equals the natural log of 1 subtract e to the power 2u. Okay, so now I have to solve this by u by itself so we can, substitute that back in. Well, it's not only just because of that, but because we have a du differential that make things, simplifying things a little bit easier. So that'll be the easier method to go with. So applying with this, if I solve everything for u on its own, we'll have 1/2 and then multiply by ln of 1 subtract e to the power w. So if I differentiate both sides, so that means du is going to equal to negative e to the power w, and then it's divided by 2 times 1 subtract e to the power w, and then dw. So now putting everything back together for our new a simplified in terms from the world of w. So now I have, this is going to be 1/2. That's just simply factoring out the half from over here. Change our bounds, so we have our new bounds that if I plug in 0 over here, then that means that's going to become negative infinity. And if I plug in negative infinity to over here, that means that's just going to approach 0. So we already see that we have to change the bounds over there. And then if I just plug in the substitution, everything in terms of the w that, substitute from here. So now what we'll have is this is going to be negative e to the power w, then times w times ln of w, and then divided by 1 subtract e to the power w dw. Simplify that even further to say that now we have to change our bounds yet again because we have that negative infinities as the upper bound and then 0 on the lower bound, one smaller than the other. So we change that, that'll cancel out the negatives. So 1/2 then times the integral from 0 to negative infinity of e to the power w, then times ln of w, well, w times ln of w, and then divided by 1 subtract e to the power w dw. Okay, so now from how do we tackle this on, let's actually now apply some integration by parts. So we're going to we have 2 variables that we're going to have to choose. One we have to differentiate, the other we have to integrate. So just going back in terms of u, which I already done before, but that's okay. Now we're in w, so it's not that big of a deal. We're going to suppose that we let u equals w times ln of w. So if I differentiate both sides, so du is equal to, so just apply the product rule. So this is going to be just ln of w plus 1 and then dw. So now we have to choose what to integrate. So dv, we'll let that be e to the power w and then divided by 1 minus e to the power w. dw, then integrate that, we have that v is going to be negative ln of 1 subtract e to the power w. Okay, so now just put everything back together. So now our new a is going to be negative 1/2 and then multiply, so u times v, so w times ln of w, and then multiply with ln of w, ln of 1 minus e to the power w, evaluate this from 0 to negative infinity. Then we still have the plus, so rather subtract and then factor out the negative and the 1/2, so that means plus 1/2 of the integral from 0 to negative infinity of ln of w plus 1, and then multiply with ln of 1 subtract e to the power w, and then dw. So what you'll notice is that if you plug 0 and negative infinity, you're going to have some things that are going to be undefined. Well, to give you just the spoiler alert and heads up that I'm going to skip the work for this and you can verify this yourself, this is going to approach simply just 0, as of course that you can fix this by taking things in terms of limits, and then of course you're going to get something of the indeterminate form, then change that so that it's a rational function, since this is just like nothing of the, rational form. You can fix that up. And if you have something of a 0 over 0 / infinity over infinity, I won't say which one's correct. That's why I'm telling you this now, that if you get that indeterminate, you can apply L'Hopital's rule, continue on further, that you're going to get that the whole difference from over here is that this is going to equal to 0. So at least that eliminates that issue. So this is what we're left to focus on. Okay, and then to continue further, so let me actually switch back to the purple for this. So now that just leaves us with this side. So now just going ahead further, one step ahead, that I'll actually just distribute the ln of w plus 1 into here, then applying linearity yet again. So I have 1/2, then multiply with the integral from 0 to negative infinity of ln of w times ln of 1 minus e to the w, then dw. Then add this with 1/2, then integral from 0 to negative infinity of ln of 1 subtract e to the w, and then dw. Okay, so simple from here that what I'll do is we'll actually do a u-sub. So let's suppose that we'll let, in this situation, we'll call this back to w again. So we'll let w equals 2 times t. So if I differentiate both sides, so that means dw is equal to 2 dt. Okay, and so with this in mind, so let's actually just plug in everything in the new, substitution. So what we have here is a new a, so I have 2 dt. I'll factor out the 2, well, the dw is the 2t, and then the 2 can come outside, and then that'll cancel out to just 1. And you'll notice that the bounds don't actually change, so that actually is nice. So I have negative infinity to 0, and then ln of 2t, then multiply with ln of 1 subtract e to the power 2t dt. And then we can continue forward with plus, same thing. So the 1/2 is gone from that 2 dt over there. Negative infinity of natural log of 1 subtract e to the power 2t, and then times 2, and then dt. So with this in mind, this is what we were dealing with so far. So I'm going to erase everything and continue forward to, simplify this integral even more. Okay, so to reiterate everything so far, we come to the observation we had that I is equal to this following expression. So what we had to do was we had to evaluate what this expression for a is equal to of the integral. And we have deduced that so far that a has come down to this following, sum of integrals. So to continue on from there, what we can do here, we have an ln of 2t that we can actually apply natural log properties yet again and split up to even more of the sum/difference of integrals. So what that comes down to, if we split this up with log properties, we have ln of 2, and that's a constant, so I'll factor out outside of the integral, so negative infinity to 0 of ln of 1 subtract e to the power 2t, then dt, and then keep going further, so we have plus the integral from negative infinity to 0 of ln of t, and then multiply with ln of 1 subtract e to the power 2t, so like this, and then just continue with this integral over here. So the integral from 0 to negative infinity of the natural log of 1 subtract e to the power 2t, and then dt. Okay, and so this is what we reduced to, and this is nice that so far this is 1/2 of this integral, so 1/2 times a. So now to put everything back together, and this is why I mentioned that we're gonna have some stuff that will cancel. So let me write everything else first, and then do the substitution after multiplying the 1/2 back into over here. Okay, so now that's everything reduced, well, rather, we actually distributed what we simplified for a back into the 1/2, and then expanded this out. So this is what I has come down to equal to. I know that looks like a pretty long expression from over there, but what you'll notice is that this is actually, some terms are going to cancel out. Specifically, we have an ln of t and then the ln of u. But in this situation, it doesn't matter, what variable you're dealing with. This is just, in the world, the dummy variable. In other words, that you can substitute this back in as so long as it works with, depending on the variable you're substituting with, rather differentiating / integrating, that if you actually notice that we have some stuff that cancel, this is going to cancel, this is going to cancel, and then the ln of 2 divided by 2, the same thing terms, this is going to cancel, and then this is going to cancel. So we're actually just left with the negative 1/2 times the integral from negative infinity to 0 of ln of 1 minus e to the power t. Okay, so that actually makes things a lot easier to simplify things down even further. So negative 1/2, then integral from 0 to negative infinity of ln of 1 subtract e to the power 2t, and then dt. Okay, so now let's actually continue forward by performing another u-substitution. Let's suppose we let y equals e to the power 2t, differentiate both sides. We have that dy is equal to 2 times e to the power 2t, and then dt. Of course, we need to get it so that dt is on its own. We can fix that by dividing by 2e to the power 2t by itself. So dy 2e 2dt 2t, and then set this equal to dt, which in other words that we set that y is equal to e to the power 2t, so we'll put that back here. So that means we have dy divided by 2y is equal to dt. So that's great that we can actually now perform some more substitutions out of that. And so from here, now we can now put in the new variable, or rather the new simplified substitution that I is going to equal to, so factor out the 1/2, so that means I have negative 1 divided by 4 the new integral. So if I plug in our new bounds, negative infinity, it's just going to be 0. If I plug in 0, that's just going to be 1 of ln of 1 subtract y, and then divided by y, then dy. Okay, so this actually looks a little difficult on how to tackle something so, elementary looking. So what you'll notice is that by definition, so this is where the special function comes in, the dilogarithm of y is going to equal to the negative integral from y to 0, or 0 to y, of ln of 1 subtract u, and then divided by u du. So, and this is for, of course, y is any complex number. So if I were to differentiate both sides, so the derivative of the dilogarithm of y, so you just take just applying by the fundamental theorem of calculus, that's just going to be equal to negative ln of 1 subtract y, and then divided by y. And it's also worth noting that another special value that will come in handy is that we know that the dilogarithm evaluated at 0 is going to equal 0. Why is that important to note? Because if I were to apply this, so this is going to be the same thing as negative 1 over 4, and then apply this, so this is going to be the dilogarithm of y, evaluate this from 1 to 0, and so far that leaves us with, so we set that the dilogarithm of 0 is equal to 0, so we have just negative 1 divided by 4, or actually because the negative cancel out from over here, so now this is strictly just positive, so positive 1 over 4. 1 over 4 and then times the dilogarithm evaluated at 1. Okay, so how can we simplify that even further? So we know that by definition, the dilogarithm of order s of y is going to be the following infinite sum representation. So our index starts from n is equal to 1 of y to the power n divided by n to the power s. Okay, so let's suppose if I plug in 2 and if I plug in 1 back into here. So that means, in other words, so it's actually, if we want to, we could write it like this. So one step at a time. So I have the dilogarithm of 1 at order s is going to equal to just the infinite sum at n is equal 1 of 1 divided by n to the power s. And now to take things a step further, so if we let s equals 2, so the dilogarithm of 1, in other words, plug this back in, is the infinite sum of 1 divided by n squared. In case you notice, this is actually the same thing as the Riemann zeta evaluated at 2. And so what does that value mean? That's actually the same thing as Basel's problem, aka pi squared divided by 6. So 1 over 4, and I'll just, if I want to, I'll just put the infinite sum notation back into here. This is n is equal 1 of 1 divided by n squared, which is the same thing as 1 over 4 times the Riemann zeta of 2, which is the same thing as 1 divided by 4 times pi squared divided by 6. In other words, this is pi squared divided by 24, which is indeed the final answer to this trigonometric integral consisting of a bunch of natural logs and then put together with the trigonometric as part of the argument of the natural logs. So there we have it. Pi squared divided by 24 comes down to a nice answer, as I mentioned earlier. So yeah, that's pretty cool if you ask me.